Now we're going to be going over sequences and series. So starting first with sequences, the definition of a sequence is a function that computes an ordered list. And there's two kinds of sequences we're going to be looking at. There's a finite sequence. A finite sequence is a function that has the set of natural numbers of the form 1 through n as its domain. And an infinite sequence is a function that has the set of natural numbers as its domain, meaning the natural numbers 1, 2, 3, 4, all the way up to infinity. So for example, the average family in the US spends $150 on food each week. The function f of n equals 150 times n generates the following terms of a sequence for the values of n, 1, 2, 3, 4, and 5, and so on. So if we plug in 1, we get 150 times 1, which is 150. For 2, plug in 2, 150 times 2 is 300, and so on. We plug in 3, 150 times 3 is 450. And we are not going to be using function notation, so we're not going to be using f of n. We're going to be using a sub n instead, and we just have to know that a sub n is actually the same thing as f of n. And we're using n instead of an x because typically we'd be using f of x for a function. We're going to be using n just as a reminder essentially that n represents a natural number. Okay, and now for the next definition here, the terms of a sequence are going to be denoted a sub 1, a sub 2, a sub 3, and so on. And the first term, a sub 1, is found by letting n equal 1. The second term is found by letting n equal 2, and so on. So we would say that the nth term of the sequence is a sub n. So let's do an example here. Let's write the first 5 terms of each sequence. The first one is a sub n equals n plus 1 over n plus 2. And we want to find the first 5 terms. That means we want to find a1, a2, a3, a4, and a5. And that means we're going to be plugging n equals 1 through n equals 5n. So plugging in n equals 1, that's going to be a sub 1. So that's the first term in the sequence. And plugging in a1 is going to be 1 plus 1 over 1 plus 2. That's going to give us 2/3 for a sub 1. Now plug in a 2 for a sub 2 here. That's going to be 2 plus 1 over 2 plus 2. That gives us 3 over 4. Plug in a 3 for a sub 3. 3 plus 1 over 3 plus 2 gives us 4/5. A sub 4, we get 4 plus 1 over 4 plus 2. That is 5/6. And lastly, a sub 5, 5 plus 1 over 5 plus 2 gives us 6 over 7. Okay, so pretty simple for finding the terms of a sequence. When we're given the function for it, we just go ahead and plug it on in. And let's do 2 more with some of these common factors of these so we can see how to compute them. So we have a sub n equals -1 to the n times n. So once again, we want the first 5 terms. So we're going to be plugging in n equals 1 through n equals 5. And plugging in n equals 1, that's going to give us our first term, a sub 1. -1 to the first power times 1, that's going to give us -1 times 1, so just -1. Plugging in a 2 gives us a sub 2. That is -1 to the second times 2. -1 squared is +1 times 2 is +2. Plugging in a 3, that's -1 cubed times 3. -1 cubed is -1 times 3 is -3. Plug in 4, +4. -1 to the 4th times 4. -1 to the 4th is +1, so that's going to give us positive 4. And then lastly, we have n equals 5, gives us a sub 5, the fifth term. Negative 1 to the fifth times 5. Negative 1 to the fifth is negative 1. So this ends up being negative 5. So we have to remember that a negative 1 to an odd power becomes negative. Negative 1 to an even power becomes positive. This little factor over here, negative 1 to the n, is what makes our terms alternate between positive and negative terms. So that's a pretty commonly seen portion of the function. All right, let's do one more. So actually, I'll pause this and just have them all filled in real quick. So I recommend you pausing it also and trying it yourself. Okay, so same thing that we were doing before, plugging in n equals 1 through n equals 5 and evaluating for the first 5 terms. We get negative 1/2, positive 1/4, negative 1/8, positive 1/16, and negative 1 over 32. All right, that brings us to the difference between convergent and divergent sequences. If the terms of an infinite sequence are getting closer and closer to some real number, the sequence is said to be convergent and to converge to that real number. For example, if we have a sub n equals 1 over n, if we wanted to find a sub 1, that would be 1 over 1, which equals 1. Just going to plug in a couple here. A sub 2 is 1 over 2. A sub 3, 1 over 3. A sub 4, 1 over 4. And just do 2 more. A sub 5 is 1 over 5, and a sub 6 is 1 over 6. So clearly, pretty obvious what's happening here. The denominator is just getting larger and larger. So what's actually going to, this is actually going to converge, and this is actually going to converge to 0. So as the denominator of a function is getting larger and larger, the number as a whole is getting smaller and smaller and smaller, and it's converging to 0. So what we can also do is we can make a little graph of these. And the x-axis is going to represent the values for n, and the y-axis is going to represent the values for a sub n. So we have our, just plotting some points here, we have the first one where an n was 1, a sub 1 was 1, so that's going to be all the way up here. A sub 2, n was 2, a sub 2 was 1/2, that's going to be right about here, it looks like. And then for n equals 3, that gave us 1/3. And 1/3 is about right here. When n was 4, a sub 4 was 1/4. So that's going to be right here. When n was 5, a sub 5 was 1/5. And lastly, for what we had, when it was 6, a sub 6 was 1 over 6. So that's going to be somewhere right here. So we can see that when we're plotting these, when we're graphing a sequence, it's these discrete points. It's not a smooth curve or anything, it's just these points. So if we kept on going and we did imagine it as a curve, we could see it would look something like this. And it's getting closer and closer to the x-axis, meaning it's getting closer and closer to 0. Okay, and now conversely, a sequence that does not converge to some number we say is divergent. For example, we have the sequence a sub n equals n squared, and let's say we want to plug in some values again. For n equals 1, we have a sub 1 equals 1 squared, which is 1. A sub 2, 2 squared, which is 4. And we'll just do a couple more of these. 3 squared equals 9. A sub 4 equals 16. And we'll just go to 6 again. A sub 5, we get 25. and then a sub 6, we get 36. So clearly, if we kept on going, we put dot, 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 we'll see that the number is just going to obviously keep on going to infinity. It's never going to be approaching a set number. And another way to say it is it increases without bound, meaning it's going to infinity. Okay, so that is a convergent and divergent sequence. So let's move on to one more thing with sequences before we go to series. And that is recursive sequences. So some sequences are defined by a recursive definition. And what that means is it's a definition in which each term is defined as an expression involving the previous terms. So each term depends on the previous terms. So let's see a couple examples here. Find the first 4 terms of each sequence. So we have our sequence a sub n equals 2 times a sub n minus 1 plus 1. So you can see that for every nth term, it's going to depend on the term directly before it. So we want the first 4 terms. So let's start with a sub 1. Well, that's nice and easy. That's given to us. And now let's go to a sub 2. A sub 2, using the definition, is going to be 2 times a sub 2 minus 1 plus 1. And simplifying this a little bit, we get 2 times 2 minus 1, we get sub 1. So now we can see that this a sub 1 is the term before it, so we have to plug it on in. So it's going to end up being 2 times 4 plus 1, which gives us 9. So a sub 1 is 4, a sub 2 is 9. Let's go ahead and find the next 2. For a sub 3, once again, we are using this definition up here. It's 2 times a sub 3 minus 1, plugging in a 3 into n. And then simplifying that, that's going to be a sub 2. So we need to use a sub 2, which we just found before this as 9. So that's going to be 2 times 9 plus 1, which gives us 19. And let's find one more here, a sub 4. That's going to be 2 times, using the definition, 2 times a sub 4 minus 1 plus 1. That's 2 times a sub 3 plus 1. And we just found a sub 3, which was 19. So 2 times 19 plus 1 gives us 39. So that is a recursive definition because each term depends on the previous term. Now let's go ahead and do one more of these. We have our definition over here on the right. A sub n equals a sub n minus 1 plus n minus 1. And we want to find the first 4 terms again. We want to find a sub 1. A sub 1 is given to us. And now let's go to a sub 2. So we can see here too, it also says for n greater than 1, meaning we're starting at n equals 2 for our definition. So a sub 2, using this definition, it's going to be a sub 2 minus 1 plus 2 minus 1. Simplifying that, we get a sub 1 plus 1. I just did the 2 minus 1. A sub 1 was 2. We just found that in the previous one. So we get 2 plus 1, and that gives us a sub 2 equals 3. Next, let's go ahead and find a sub 3. That's going to be a sub 3 minus 1 plus 3 minus 1. And that's going to give us a sub 2 plus 2. And we just found a sub 2 in the previous one, which was 3. So that's 3 plus 2, which gives us 5. And let's do one more, a sub 4. using the definition a sub 4 minus 1 plus 4 minus 1 equals a sub 3 plus 3, just simplifying it once again. A sub 3 we just found was 5, and 5 plus 3 gives us 8. Okay, so those are recursive definitions. And now let's move on to series. A series is going to be the sum of the terms of a sequence. So a sequence we can think of it as a function, and we can also think of it as an ordered list. A series is the sum of the terms of a sequence. We are typically going to be writing this using summation notation, and that's going to be using the Greek letter sigma, capital sigma, so that's going to be this symbol right here, and not to get confused with lowercase sigma, which looks like this, which is looks completely different. So summation means adding. We're using the capital Greek letter sigma, and that we're going to end up getting two kinds of series here, an infinite series and a finite series. Starting with a finite series, we can abbreviate and just call it S sub n, and that's going to be the sum of all of the terms in a sequence, a sub 1 plus a sub 2 plus a sub 3, all the way to however many terms there are in the sequence. And the way that we write this is using this summation notation, the sigma, and like it's mentioned down here, the I is called the index of summation. That's telling us the integer value where we're starting, and this upper symbol up top, which is an n obviously for now, it's going to be typically a number. That's going to tell us where to end. So I equals 1, we're starting at 1, and then we keep on plugging in numbers into this expression here, and we're adding them up until we get to I equals n in this case. And then we can also have an infinite series. An infinite series is going to look exactly the same. That's going to be S sub infinity. We're going to be adding up all of these terms of the sequence, but it's going to be for an infinite sequence, and it looks exactly the same with summation notation, except the upper bound here is infinity. Okay, let's do a couple examples. We are going to find the sum of this series. So we have sigma and this index here. Notice that that index is a k and not an I. It means the exact same thing. We are starting with k equals 1, and we're going up to k equals 6. So our indexes here are going to be 1, 2, 3, 4, 5, and 6. What that means is we have to plug it in this expression one at a time and then add up the result. So we're going to start with k equals 1. So we're going to plug in a 1 into this expression. So 2 to the first power plus 1. And it's a summation, so we're adding. Now we're going to plug in a 2 back into this expression. So 2 squared plus 1. And now we're adding again. Plug in a 3, 2 cubed plus 1. Plug in a 4. 2 to the 4th plus 1, plug in a 5, 2 to the 5th plus 1, and I'm just going to move this all over here. And lastly, plug in a 6, so 2 to the 6th plus 1. So we can see that this first one represents k equals 1, k equals 2, k equals 3, k equals 4, k equals 5, and k equals 6. So all we have to do here is simplify each one individually and then add them all up. So for the first one, let's do a little bit of it in our head. We get 2 plus 1, so we get 3. Second one, we get 4 plus 1, so we get 5. Third one, 8 plus 1, we get 9. Fourth one, 2 to the 4th plus 1, so 16 plus 1, we get 17. Next one, we get 32 plus 1, 33. And last one, we get 2 to the 6th is 64. 64 plus 1 is 65. So all we have to do now is go ahead and add up all of these numbers, and we should end up getting 132. 2, which is our answer. Okay, and let's go to the next one here. So it's going to look a little bit different, but it's going to be the same concept. Let's write the terms for the series, and we're going to evaluate when x1 equals 2, x2 equals 4, and x3 equals 6. So we have this expression, 6 times xi minus 2, and the I is starting at 1 and going to 3. So we're going to be evaluating it for 1, 2, and 3. So let's go ahead and do that. Let's plug in a 1. That's going to be 6x sub 1 minus 2 plus summation, so plus once again, 6x sub 2 minus 2. So that one was for plugging in a 2. And now lastly, plugging in a 3 where we end, 6x sub 3 minus 2. And there we go. There's our 3 terms for this series. And we want to evaluate this now for x1 equals 2, x2 equals 4, and x3 equals 6. So let's go ahead and plug those in. That's going to be 6 times 2 minus 2 plus 6 times 4 minus 2 plus 6 times 6 minus 2. And once again, let's go ahead and just simplify these individually and then add up those results. So the first one, 12 minus 2 is 10. Second one, 24 minus 2 is 22. And the last one, we have 36 minus 2 gives us 34. And we add all of these up. 10 plus 22 is 32, plus 34 is 66. And that is our answer. Okay, so it's a little bit different format than the other one, but same exact concept. And for this next example, it's going to be, once again, something that's a little bit different, but same idea. So the following infinite series can actually be used to approximate pi. There are tons of approximations for pi, and this is going to be one example of them using a series. And it's an infinite series, meaning it goes on forever. So let's approximate pi by finding the sum of the first 4 terms. Okay, so the expression here, the equation, or the series, says pi to the 4th power over 90 equals 1 over 1 to the 4th plus 2 over 2, 1 over 2 to the 4th plus 1 over 3 to the 4th, and so on. So we're going to use the first 4 terms, and let's rewrite that out. So it's going to be pi to the 4th divided by 90 equals 1. I'm going to put approximately because we're approximating, so I'm going to use the little squiggly equal sign. 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th. So if we type this in a calculator, we're going to end up getting that pi to the 4th over 90 is about 1.078751929. So plug those numbers on the right into the calculator, we get that. So we're trying to find an approximation for pi. That's not pi, right? That's pi to the 4th divided by 90. So what we have to do is kind of solve for pi like we'd be solving for x. And we would have to multiply 90 on both sides. We would get pi to the 4th is approximately 90 times this 1.078751929 number. And then to cancel a power of 4, we have to raise both sides to the reciprocal of 4, which is 1/4, which means we're taking the 4th root of both sides. So that's going to be the 4th root of 90 times this 1.078751929 number. And if you are typing this in the calculator, you're either going to have to change the root for the radical sign, or you can use an exponent of 1 over 4. Either way, we should end up getting pi is approximately 3.139. So obviously we know this isn't the exact value, but this is an approximation using the first 4 terms of an infinite sequence. And already 4 terms obviously is not a lot of terms. This approximation is pretty good. We're pretty close to 3.14-ish. So it's not that bad of an approximation. So obviously the more and more terms we use, the more and more accurate the approximation is going to get. Technically, it's not 100% accurate unless you're using all infinite amount of terms though. Okay, so let's go ahead and look at this last thing here with some of these summation properties. So here are a couple important properties that can be useful when we're trying to evaluate series. We can do some nice shortcuts. So the first one with A, we have the summation of some constant C from 1 to n. So all you would have to do here is there's nothing to plug in. So you'd be adding C n number of times. So instead of adding C n number of times, all you have to do is multiply n times C. Okay, and then the next one is if we have, for B here, if we have a constant times another factor that does depend on the index I, we can bring that constant out front and just multiply it by the answer afterwards. It's essentially just factoring it out front from all the terms being added. And the next one, if we have a summation of two different terms inside of here that both depend on I, we can do them separately and give them both their own summation. And same thing with subtraction, we can give them both their own summation with subtraction also. And then here's also a couple other little rules that come in handy. If you are adding up, so let's just look at the summation and then we'll make sense of it. If you have the summation from 1 to n of just I, what that means is you're just adding up 1 plus 2 plus 3 plus 4 all the way to n. Instead of having to add that up, because that's a pain in the butt, there's a shortcut to it. And the shortcut is you multiply n times n plus 1 and you divide that by 2. So that is a lot shorter than adding up all the numbers between 1 and n. And for another shortcut here is if you have the same idea but with I squared. So that's 1 squared plus 2 squared plus 3 squared all the way to plus n squared. You do not want to have to add all those up by hand. The shortcut is you multiply n times n plus 1 times 2n plus 1 divided by 6. And you can just evaluate that whole thing in one big swoop. And then the last shortcut is I cubed. So same idea, 1 cubed plus 2 cubed plus ... all the way to n cubed. The shortcut is you do n squared, multiply it by n plus 1 squared, and divide it by 4. So these little properties come up from mathematical induction. Not going to get into it right now, but if you wanted to go look that up, it's mathematical induction. You can see a nice proof for these. Okay, let's do just a couple more examples using those ideas. So let's use the summation properties and rules to find each sum. So the first one, we have the sum from I equals 1 to 40 of just 5. So this rule is going to be the first one that we mentioned on the previous page for right here. If you have the summation of a constant, you just have to multiply the n value by that constant. Because this does not depend on I, there's nowhere to plug it in. So what we would actually be doing is just 5 plus 5 plus 5, and we'd be adding this up 40 times. So let's not have to do that. All we have to do is know that this is the same thing as 40 times 5. So this is going to be the sum 40 times. So 40 times 5 ends up giving us 200. Okay, so knowing this shortcut makes it more than 10 times shorter. So let's go ahead and see the next one. We have the summation from I equals 1 to 22 of 2i. So first we notice that we do have an I here, but we have this 2. If we didn't use this shortcut, we'd get the answer perfectly fine. We would just be making it one step more annoying, making the numbers a little bigger. We can essentially factor this constant out front and write it like this. So it doesn't really look like factoring when we have the summation. If we had them all written out, it would be like a GCF factor of 2 pulled out front. Okay, so now we have the summation from 1 to 22 of just I. This is also going to be a shortcut. It's going to be this shortcut right here, the summation of I. So we're going to do n times n plus 1 over 2 for it. If we didn't do that, we would have to add up 1 plus 2 plus 3 plus all the way to 22, which isn't the worst thing in the world, but this will be a lot shorter. So our shortcut is going to be 2, and that's just the 2 that's out front, times n, which is 22, times n plus 1, which is 22 plus 1, divided by 2. Okay, so that's the shortcut from the previous page. And what we can see here, which is kind of nice, is that 2 divided by 2, they will cancel, and we get 22 times 23. And 22 times 23, we end up getting 506. Okay, so definitely a lot shorter for that one. Let's do one more. We have the summation from I equals 1 to 14 of 2i squared minus 3. So there's a couple things that we could do here. First, we can give each one of those terms its own summation and make this the summation for 2i squared minus the summation for 3. And next, we can actually take this 2 out of the first one and bring it out front, just like we did on the previous one. So it's going to be 2 times the summation from 1 to 14 of I squared, and then keep the second one the same. And now we can use some shortcuts. So the one on the right is a constant, so that's just going to be n times the constant, so 14 times 3. The one on the left, we have an I squared. The I squared is going to be this from the previous page, the n times n plus 1 times 2n plus 1 divided by 6. So let's go ahead and set this up now. And we're going to have 2 times, and using the shortcut for this I squared one, the shortcut's going to end up being n times n plus 1, so 14 times 14 plus 1 times 2n plus 1, so 2 times 14 plus 1. So that's pretty messy, but not too bad. Divided by 6. Minus the shortcut for the other one was 14 times 3. And all we have to do is evaluate this, so a little bit annoying, but it's a lot better than actually having to write out each individual term. So I'm assuming that we can do order of operations correctly. We should end up getting 1,988. Okay, so that is it for this section with sequences and series.